Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. There is so very much to learn about creating PC boards, and DIPTRACE has so very many great features, including 3D rendering of your board. I cannot possibly even begin to cover even a fraction of all of it, but I will give you enough to get you started. Now, here's one very important point that you must keep in mind throughout the entire process of designing your PC board. The view that you see on the screen is you looking down through the board from the top. Now, that's true even when you're placing traces on the bottom of the board. It is always looking down from the top through the board, unless you choose to show it mirrored. Now in this video, I'm going to walk through the entire process, beginning to end, of designing a real PC board to create our little 3-input mixer. Now this will include all of the steps along the way, up to and including ordering the board from my favorite board fabrication house, OSH Park. In the last video, I covered the basics of the anatomy of PC board, including all of the various things that we will be using here today. If you missed that very important video, I've put a link to it up in the corner for your convenience. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Before we even open the PC board design software, we have to know where the board is going to live and how it's going to live there. Well, Ralph, here's the enclosure that we want to use for this awesome mixer that you all have designed. I hate to break the news to you, but there is no way this mixer is going to fit into that tiny enclosure. But this is what we had envisioned from the beginning, and that may be, but there is no way a 3-input mixer with everything else you specified is going to fit in there. Here's the enclosure that the engineering team has picked. It makes for a comfortable user interface, and it will be easy to get everything in there. And besides that, see the way awesome mounting flanges that can be used to secure it in place somewheres? Well, I suppose, but we really had our heart set on this cute little enclosure. Maybe we can use it for something else sometime? Yeah, it's cute. Who knows what the future holds? Now that we have our enclosure nailed down, the very first thing that we have to do is to determine all of the mechanical aspects of the board, which includes things like, well, how big the board is going to be. In other words, how is it going to fit inside the enclosure? And then the physical locations for things like mounting holes, controls, indicators, connectors, and other similar things. The temptation is to locate everything relative to the edge of the board. But the reality is the actual physical dimensions of the board might vary by as much as 20/1000ths of an inch or 1/2 millimeter. Now, that doesn't seem like a lot, but it can make a huge difference in fit between the board and the enclosure. So how do we avoid this? We establish a specific reference mounting hole, and then all other measurements are made relative to this mounting hole. The relative distances for mounting holes and the positions of components and the like are held to a much higher tolerance than the dimensions of the board. So now let's take a look at our enclosure. So here's our enclosure. It's a Hammond 1591 ES-FL BK. I chose this one for its convenient size and its affordability. Now, admittedly, there were a lot of much prettier enclosures that I could have chosen, but the cost was well beyond anything that I was willing to pay. According to the drawing for this enclosure, the inside dimensions that our board could fit in are 6.622 inches or 168.2 millimeters wide by 3.472 inches or 88.2 millimeters high. We want a little extra wiggle room, so we do not design the board to just fit into the enclosure. The other consideration is cost. Remember, the larger the board, the more it's going to cost to have it made. So we'd like to try to make the board as small as possible, yet without making it impossible to get everything in there. So after much consideration, I'm going to shoot for 6 inches or 152.4 millimeters wide by 3.3 inches or 83.8 millimeters high. Now let's place the board outline. We click on the Objects menu item and then the Place Board Outline item in the pop-up menu. At this point, the places you click on the design window will define the corners of the board. Now there are two ways we can place the board outline. The first is by carefully clicking on the right spots. And then when you click on the starting point again, it completes the outline. The second way is to randomly click on 3 spots and then back to the origin. Right-click to get out of the Place Board Outline mode, right-click on the outline and select Board Points from the pop-up menu. Now we can type in the specific points that define the board outline. With the board outline defined, we have to locate the mounting holes for the board next. I will be using flathead 440 screws to mount the board to the enclosure. A close metric equivalent would be a flathead M3 by 0.5. I will have to determine the length when I address the mounting depth of the board, which will also affect the height at which I mount my LEDs. For a 440 screw, I will need a hole size of 125 mils or 3.175 millimeters. To clear any possible hardware like standoffs and nuts and the like, we'll need at least 250 mil or 6.25 millimeter keep outs around them. I've decided to use a total of 6 mounting holes. 4 of these will be located in the 4 corners of the board, and then 2 midways down the long axis of the board. To place these, we can either carefully click on the right spots for them to reside, or we can randomly drop them and then edit their positions. Click on the Objects menu item and then the Place Mounting Hole option in the pop-up menu. Optionally, you could also click on the Place Mounting Hole icon in the toolbar. Edit the specifics of the hole, its hole diameter, and the route keep out in the upper right-hand corner of the DIPTRACE window. Now, a mounting hole will be placed in every location you click. I'm going to do the random drop and then edit approach. I have located all of these as shown. I'm going to place some dimensional lines in the design to document and verify the position of the mounting holes. When placing dimensions, the dimensions are placed on a layer commensurate with the current active layer being displayed. If the top layer is selected, then the dimension lines will be placed on the top dimensions layer. If the bottom is selected, then the dimension lines will be dropped on the bottom dimensions layer. Now, with that said, if you open the dimensions properties, you can move the dimension to any layer that you might choose to put it on. Now I'm going to place all of the horizontal dimensions first and then the vertical. Notice how I choose the far item and then drop the line so that I have a dimension line down through both holes that have the same dimension. As you can see, the text is really small, and the dimensions are in the default unit for the design, which is mils or thousandths of an inch. I'm going to display my dimensions in inches, and I will change the font size to something that I can actually read. Maybe, I don't know, an 8 font size. We can make these dimension lines disappear by going to the Layers tab in the upper right corner of DIPTRACE window, and then unchecking the layer where they reside. Now that I have all of the mounting holes located and the dimension lines drawn, the next step is to figure out where all the controls and indicators will be. This decision starts with deciding which side of the board everything is going to be on. If I put all of the parts on one side of the board, then all of the ICs and the resistors and the like will all be sandwiched between the board and the front panel, making troubleshooting or measurements and the like nearly impossible without having to remove the board from the enclosure. And who wants to do that? So I'm going to put all of the controls and indicators on the bottom of the board and everything else on top. The tricky part about this is that the board perspective will be mirrored. This means that left will be right and right will be left from the perspective of the controls. So if I want channel 1 level control on the left as seen from the front panel, it must be on the right as seen from the top of the board, which is the back of the front panel where all of the other parts are going to be living. Now, I'm not going to go into detail about how I come up with the positions of the controls and indicators here, but I'm going to show you how I located them on the board. And this process begins by importing the information from the schematic so we have parts to place. We are done with the dimensions for now, so I'm going to turn off top dimensions layer. To bring in the schematic information, I click on the File menu item and then hover over the Renew Layout from Schematic, navigate to and click on the By RefDes option. Using the Open dialog box, navigate to the schematic file and click on the Open button. All of the parts are placed on the right of the board outline and all on the top layer. Now the first thing I want to do is shut off all the rat lines. We're going to want them later, but for right now, they're kind of in the way. So go to the Object tab in the upper right hand corner of the DIPTRACE window and uncheck the rat lines item. Now I want to send each of the LEDs and the controls to the bottom of the board. I right click on the component and then select Change Side from the pop-up menu. The component seems to disappear, but it's on the other side of the board now. Once done, I change my view to the bottom of the board by pressing 2 on the keyboard. Now, one by one, I right-click on the component, select Properties from the pop-up menu, and then enter the physical position of the component in the Properties dialog box for the component. This locates the component reference point at the specified location relative to the lower left-hand corner of the board. Yes, I did say that we want dimensions relative to a mounting hole, but this is for the machining of the enclosure, not the design inside the board design software. One of these I have to rotate to get in the right position. So you select the component and hit R to rotate it 90 degrees counterclockwise. We are now looking at the back of the front panel. To get a feel for what it'll look like from the front of the front panel, I will mirror the view. Click on the View menu item and then the Mirror from the pop-up menu. Here's Channel 1 control, Channel 2 control, the Channel 3 control, and the output control with its level meter. I will unmirror the view for the next phase of our design. Now let's place dimension lines for the folks that have to machine the enclosure. We will print these later for them. I will leave them in mils for the machining folks, but make the font larger so that they're readable. We do not want any of the things that we've placed on the board to be moved. We can move all sorts of stuff all around them, but these things need to be anchored in place. To do this, we select everything, the mounting holes, the controls, the indicators, all of that stuff. Then we right-click on one of them and select Lock Selected from the pop-up menu. Done. Now, I'll pop over the top by hitting 1 on the keyboard in preparation for placing the rest of our components. Using the schematic as a guide, place all of the active components in positions relative to the controls and indicators that we've already placed. Don't worry about their exact placement yet. Now, let's turn on the ratlines and optimize them. To optimize the ratlines, click on the View menu item and hover over the Ratlines option in the pop-up menu and select Optimize, or just hit F12. Using the ratlines as a guide to see what pins will be connected where, fine-tune the position of the active components to minimize crossover points. It is at this point that we will most often discover that we have to make changes to which section of a particular component is used for what to make routing easier. I discovered in this process that the output amplifiers will work better for me if I swap the sections. So let's update things to fix this. I open the schematic and make the necessary changes. I save the schematic. Now we go back to the PCB design and renew the layout from schematic. Done. I suggest optimizing the ratlines again and verifying that the changes you made had the desired effect. Now we get to place all of the rest of the components. We also want to adjust the position of the silkscreen reference designators as needed to be sure they make sense and are visible. Like in the schematic, hit F10 to enter the Move Text mode and R to rotate them as needed. One note, the components associated with the input pins of op-amps should be placed as close to the op-amp input pins as possible to avoid creating antennas for noise and interference. I'm not going to have you watch this whole process. Instead, here are the finished results of component placement and reference designator beautification. Notice how relatively simple all the ratlines are. And when everything is properly placed and component sections selected right, this is your goal. Now, let's start connecting things together. Well, there are two ways that we can connect everything together. The first option is using the auto router function. With this option, you can just kind of sit back and watch the program do all of the hard work for you. But the downside is that you will have to go back and clean up a lot of stuff. In my experience, I spent almost as much time cleaning everything up as if I had just routed everything myself, so I tend not to use the auto router. But if you want to give it a try, this is how to do it. The first thing you need to do is place your ground plane copper pores on both sides of the PCB. If you don't do this, it will create ground traces everywhere, and you really don't need this. To do this, we hit the 1 key to select the top layer. Then we click the Place Copper Pore icon on the toolbar. Now we draw the extents of the copper pore by clicking on wherever the indices will be for the pore. Just like we did when we placed the board outline. And just like that, these points can be edited and adjusted as needed later. It is complete when we click once again on the starting point. A dialog box opens, And it is here that we tell DIPTRACE how to connect the pore to pins and what net the pore is associated with. Click on the Connectivity tab. Locate the Connect to Net field, click on the down arrow on the right, and then select GND from the list of nets associated with this design. This will make the pore a ground plane. Locate the Thermals field and select anything but Direct. I choose 4-spoke. Make sure the Direct Connection for Vias checkbox is checked. Then click on the OK button. The pore gets filled in, and all of the pins that are connected to ground are connected to the pore via the thermals. Now we can press 2 key and select the bottom layer and repeat the process. Or I click on the edge of the copper pore and I copy this. Then I send the copper pore to the bottom. Next, I paste the copper pore in place and update both the top and bottom pores. This way, the two pores are exactly the same size and exactly in the same place. The second thing we do is we start the auto router and watch it work. To do this, we click on the Route menu item and then the Run Auto Router option in the drop-down menu. Then we sit back and watch it work. When it's done, we see all these red circles everywhere. Well, these are DRC or Design Rules Check Errors. The first step in clearing these is to update the copper pores. So the third thing that we have to do is, well, update the copper pores. Hit the 1 key to select the top layer, click on the edge of the pore to select it, then right-click on the same edge and select Update from the pop-up menu. Hit the 2 key and then go to the bottom layer and do the same thing. Now we have to rerun the DRC check, so click on the DRC icon in the toolbar. Now we get a clean bill of health from the DRC checker. But this does not mean that we are free of issues. Notice all of the rat lines in the board. So now we get to do the fourth thing, fix all the stuff that needs fixing. The process of doing the auto routing sliced the ground plane up into smaller pieces, creating islands. Pins that were connected to ground are no longer connected. These are the things we need to fix by moving traces and vias and stitching the top and bottom ground planes together with static vias attached to the ground net. And thus, my preferred method is still manual routing, which we'll talk about next. Connecting things together manually means that we have to think three-dimensionally. I mean, we have the X and the Y directions on any given layer, but then we also have the Z direction when we send a signal to another layer. So why switch layers? Well, what if a trace for one signal prevents the trace for another signal from getting to its destination? By switching layers, you can go under or over the blocking trace and still get to your destination. In some cases, you might have to do this more than once. First, I select the top layer because this is where all my surface mount components live. I hit 1 on the keyboard. Now I'm going to turn off all of the rat lines for the ground and power pins for now so that my view is a little less crowded. The ground will be taken care of in due time by the copper pore that I'll be putting on the board, and I will route the power traces last. Now, some may argue that the power traces should be done first. Well, this is all a matter of style and preference. To turn off the rat lines for a specific net, right-click on a pin that is associated with the net and select Hide Net Rat Lines from the pop-up menu. Now let's zoom into channel 1 and channel 2 input amplifiers chip U1 and place some traces here to connect things up. Notice that when I hover over a component pin, it turns red, and everywhere that it's supposed to be connected also turns red. I will be routing this using DIPTRACE's default trace width settings. We begin by clicking on the Route Manual icon on the toolbar. I click on a pin that I want to connect to, and I'm dragging a trace around. I anchor a point by clicking on a spot and then continue to draw the trace to where I want it to go. See how easy it is to connect things up? Oops! Now we have a little problem. I have to get this connected down to the potentiometer, and well, there are traces in the way. So how are we going to do this? Well, we bring the trace out as far as we can, anchor it in place by double-clicking on a spot. Now we drop a through via to the bottom of the board by pressing the 2 key. We can now complete our routing along the bottom of the board to where we need it to go. I press the 1 key to go back to the top and continue this process. Once I have all the signal traces complete, I will route all of the power stuff using a 30 mil or 0.76 millimeter trace. I want nice wide traces for power to minimize their impedance and voltage drops along the way. Now, I don't expect you to sit there and watch me as I lay every trace on the board. So let's do a time jump. As you can see, now I have all the traces in place. I've turned on all of the rat lines. You can see all of the ground connections that haven't been made yet. The next step is placing the copper pores for the top and bottom ground planes. I am going to go through the same process now that I did in preparation for using the auto router. We have to remember the design rules, which do not want this copper pore within 25 mils of the edge. You will notice that even after the copper pore is put into place, there are still rat lines showing. This is because there are islands in the copper pore. While part of the overall ground net, they are not electrically connected to one another. So how do we fix this? Well, the first thing is we look for ways to create openings where the copper pore can pour through into the island by moving traces and vias. And the second thing that we can do is use the bottom ground plane as a means of connecting these islands to the overall ground net. We do this using static vias assigned to the ground net. While we're at it, we also want to stitch the top and bottom planes together even if there are no islands. This is how we place these static vias. I click on the Place Static Via icon on the toolbar. Now, everywhere I click, I drop a via. I check the other side of the board to make sure that I'm not dropping a via on top of some signal trace. But you know, these vias aren't connected to any particular net, and they're not going to do us any good until we add them to the ground net. To add a static via to a net, we right-click on the via and hover the mouse pointer over the Add to Net option in the pop-up menu. Then select Select by Mouse Pointer option in the pop-up menu, move the cursor to a component pin that is part of the ground net, and click on it. Done. Now, this has to be accomplished for each of the static vias. Unfortunately, it cannot be done en masse. Notice that at the end of this process, all of my rat lines have disappeared. Now this means that everything is connected everywhere. To be sure that both ground planes are the same potential everywhere, it is a good practice to stitch them together with additional static vias assigned to the ground net. Now, you don't need to watch me do this. Here is the completed board with all of the vias and traces and ground pores. Now, I think I'm done, but I have to run some verification steps before I'm convinced. There are two basic verification steps that we have to perform. The first are the design rule checks, or DRC. This checks clearances and the like to be sure everything is where it should be. This is very easy to run. Just click on the DRC icon on the toolbar. The next check is the connectivity verification. This makes sure that everything is connected to what it's supposed to be connected to and is not connected to things that they're not supposed to be connected to. To run this, click on the verification menu item and then select Check Net Connectivity option in the drop-down menu. Be sure that the traces, shapes, and copper port checkboxes are checked in the dialog box, and then click on OK. With no errors, we are good to proceed to generate the files that we will need to have the PC board fabricated for us. There is a specific set of files that a PCB fabricator needs to create your PCB. The first is actually a group of files called Gerber files. No, we're not talking about baby food. These are the de facto industry standard files which describes your PC board. They were the brainchild of Austria-born Heinz Joseph Gerber, the founder of Gerber Systems Corporation back in the 1950s. They are plain text, two-dimensional vector image files which describe all of the images that make up the various layers of the PC board. I've put a nice link in the description to an article if you would like to read more about this. Each layer of the PC board has its own Gerber file. So, on a two-layer board, you can expect the following Gerber files to exist. There's the top silk screen, the top solder mask, the top copper, the bottom copper, the bottom solder mask, the bottom silk screen, and then the board outline. For each additional layer, you add another file. But we can't stop there. So far, we have only the artwork of the various layers. We have no drill holes in the board for vias, through-hole pins, and mounting holes. And this is where the NC drill file comes into play. The NC drill file is a plain text file which contains the set of instructions used by automated machines that drill the hole in the PC boards. If you want to learn more about these files, check out the link that I've put in the description for you. Okay, so now let's see how we get these out of our design in DIPTRACE. So here we are in our design. Now before we begin this, click on the View menu item. If the Flip Text Automatically is not checked in the drop-down menu, click on it to select it. Now we're ready to export our design files. To export the required Gerber and NC drill files, you need to click on the File menu item, hover over the Export option in the drop-down menu, and select Gerber from the pop-up menu. We have to set up what files we're going to be exporting, and to do this, we click on the Files button. My files are set up for a two-layer board that I'm going to be sending to OSH Park for fabrication. Now, they want very specific file extensions for each of the files. I've put a link in the description for the OSH Park naming convention. To change the entries in the table, click on the row you wish to change and then enter the new data in the fields below the table. Notice the column Include into Export All. I entered Yes for only the files needed for OSH Park fabrication and No for all the rest. Make sure that both checkboxes are unchecked and the Export All options at the bottom of the dialog box, and then click on OK. Next, we click on the Apertures button and then the Auto button in the pop-up dialog box. Now, we're just about ready. Click on the Export All button at the bottom and select Zip Archive Gerber plus NC Drill from the pop-up menu. Tell DIPTRACE where you want the file to go, and the name you want to give it, and click on the Save button. Bang! It's done! Click on the Close button, save your project, and we're ready to order boards! Ordering boards from OSH Park is as easy as drag, drop, review, and checkout. Now, I've put a link down in the description for OSH Park's website. All we have to do is drag the zip file that we created using DIPTRACE over into the website and drop it there. From here, we just follow their awesome directions and you're good to go. So, the boards are off to OSH Park for fabrication. Now, OSH Park is very, very good about giving you status reports at each step along the fabrication process. Now, it'll be a couple weeks, but they'll be here. In the next video, I will be populating the board with parts, so it'll be a quick tutorial on working with surface mount parts. Then will come the initial testing phase and the completion of the project. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-oots.